share the screen. Okay, so we are now sharing the screen. Okay, so in the first half of today, we learned how to do fine tuning, right? To implement that using the workflow of Hugging Face for both a GPT and a BERT, but we were using some data, a data set that's provided, essentially wiki text. But usually, what you might want to do if you have your own business idea or startup or something like that is you'll have your own data, right? And that's what you want to feed into the model. So with these workflows, the best thing, as I said, is just take your data, put it in the format that's expected, and then once you do that, all the other steps are going to work because it's just text at the end of the day, right? And so that's what we're going to discuss in this next example. Again, I'm going back to this. Remember, the link brings you here, and then we're in GPU required, and I made some tweaks this year, so the 2026. All right, so we covered these two examples already, fine-tune a GPT and a BERT. Now we're just going to cover this example. My own data set, as you can see, I also have a TXT file, which I need because this is going to be my data. Okay? So you would need to download this and connect it to Colab somehow for this to work. So I think I already did this. So let me check my Google Drive. Anyway, I think it's already there. If not, we'll just add it. So let's open up Colab then. We're going to open up Colab. We're going to have to mount the drive because we need that data set. Imagine you collected that data somehow. Okay, so let's have a few. All right, so I'm going to click on this. Mount. Second. Click on drive. It should be in here. All right, so maybe. All right, so let's just download it then. So notice is the format is just like this. I took a notepad, sentence one, enter, sentence two, enter, sentence three, enter, sentence four, enter. That's essentially the whole format. You can see that there. Some of them are longer. Okay, so let's download this. Okay, so RC train TXT. Load it onto Google Drive. Downloads rctrain.txt. There it is. Loaded, right? Okay. Now we go to Colab. can also do it that way, I guess. Do the 3 dots, copy path. So it should be there, right? That's the path for it. Let me do this again. Oh, there. Okay, so here it is now. All right, so I'd rather use this approach. So I'm going to take the copy path, and there it is. Right, so that's my file. So now, as I said, the key thing is, you know, open a notepad.txt, put a paragraph or a sentence, hit enter, and then you get the next one, enter, and the next one. That's essentially it, as you can see here. So I have 4 rows, 4 sentences, 4 samples, whatever you want to call them. Okay, so now let's take a look at the code. And all we want to do is bring in this text, our own text, and just make sure that it appears in the format that we have, that Hugging Face expects, and then everything else should work in the workflow. So now we're going to go back to 2026. I have the script here, my own data set. You can see here, we're going to bring in load dataset, the usual load dataset, just so that we can confirm format. Okay, so I'm going to hit run, right? Okay, there it is. Brought it in again. Then we can, print out the data set. So you can see that's essentially the structure of it, right? So we want it to be in something that fits into this data set dictionary data structure that they have. So we've got here a test, a train, a validation. We have this labeled text, and then the number of rows representing the individual samples. So when we load our data, we don't have to have all that information, but the information that we do have, we want it to be sort of in this format. And then everything else should work. That's essentially it. So now, let's add a few more cells here. Okay. Just for completion. So now, for instance, let's take a look at an individual sample and train. Right, you can see this is just showing a train set text. There's 36,718 sentences or paragraphs in there. Okay, so here, then, we can just show a few. And you can see it's essentially showing the new line character at the end of the first one, right? The new line character at the end of the second one, and then the last one, the third. That's essentially it. Okay, so again, I'm just showing here the format of what the format is when you're using a provided data set. Now we do the part where we load our own data set, and it's really just this one function down here. So we use this thing called load data set, right? Provided from data sets, we have this function called load data set, and that's it. It does all the heavy lifting for us. Okay, so notice I'm going to grab this. Okay, so let's look at, let's bring it in first. Make sure there's no errors. Okay, so this green check, good. And as you can see, its content drive, my drive, RC train. Content, drive, my drive, RC train. So as you can see, that's my path, the path to my file. Okay, to keep things simple, I just used the same file for both train and validation. But obviously you could have a second file, right, called validation. And essentially you just say that, we use the function load dataset, we specify that this is text, we specify the data files, and we indicate that one is train, one is validation, and that's it. When we looked at this originally, right, we had test, train, validation, and then we had text, the features are text, and the number of rows, right? So that's exactly the format that we're trying to emulate. So now that I have my own data sets, essentially that means that using load dataset, I'm able to load my data into the proper format that Hugging Face is expecting. You guys see that? So we can corroborate that just by running a few more things, but it's ready to go. So now I can print my own data sets, for instance. And you can see it looks exactly like the other one. And that's the key, right? So if you can create this with your own text, you're ready to go. That's the magic. So now you can see I have data sets. I created my a train one, a validation. They're both the same because I kept things simple. Each one has 4 samples and the feature name text. So I can just look at one or a few. So I can look at all 4, for instance, just to kind of further illustrate. So I take my own data sets from train, and I'm going to look at all of them. And you can see it looks exactly like when I was using their data set. I have 1, 2, 3, and 4. And that's it. So now you have all the elements. So if I decide to give you a 4th homework, right, where I ask you to get some text data off the web, your own data set, and then I say grab a GPT and fine tune it with your own data set, and then let's use the model for inference, you can totally do it. Any questions, guys, on this? All right, so at this point, I think you guys are capable of fine tuning GPTs and fine tuning a BERT, okay? So that's using the Hugging Face tool. The challenge, as I said, is always going to be, the GPU power and all of that. So there are constraints. Okay, any questions on any of this? All right, great. So it seems like you guys get it. So now we're done with this part. So this gives you the tools to really deploy, large language models to train them in the fine-tuning process. Now in the second half of today, we're going to go back to more of understanding, right? So our goal today is to understand the BERT model, and the best way to understand these models is just to do a baby BERT, right? So it's, we simplify it. For those of you that have taken 520, this is highly consistent with that. For those of you that hopefully will take 520 later, we get into a lot of the details of an actual GPT, but this is just to kind of cover the BERT. All right, so I'm going to close this Colab, and I'm going to close this as well. All right, so let's go back to Brightspace and the table of contents. All right, so we are still in this module, all right, and we're going to wrap up this module today, here by clicking on Baby BERT. So I put together this README file on GitHub. It's got the notes, explanations, and then I will just go into the code. So I have 2 code examples and to illustrate, let's look at this. So this is something we covered last week, but I'll just start here again. So remember, there was the transformers paper, and that was for language translation. It had an encoder and a decoder. Decoders are the GPTs, encoders are the BERTs. So in this, our focus right now is the BERT model, which we will need BERT models to understand reinforcement learning and to be able to implement some aspects of it. So once they decouple the encoder, then we scroll all the way down to where I have the BERT part. Yeah, encoder-only models, right? So one nice thing about encoders and decoders, they're very much the same thing. They use attention mechanism, as you will see, so K, Q, V, all that good stuff, right? So that's still there. And really all that's different is like the last layer, right? So we have to add, a layer of predicting a word or a layer of predicting just a score, right? And that's like the power of these kinds of things. So so what we want to remember, so this is from the previous lecture, is these two ideas. So I have these two diagrams, if you remember. So BERTs were bidirectional encoder representations from transformers, paper from around 2019 by Google, I believe. But essentially they took an encoder, remember, and they're like, what do we do with this? Okay? Because the other part is for generating sentences or answering questions. So what do we do with it? So they created these two architectures where essentially they take a sentence as input, but they would mask one of the words, right? And then they would predict that word here by adding a feed-forward layer and then essentially a vector of all the possible words. And so they would calculate a probability distribution, right? And say this is the word. So remember, this is they created this setup and then they train. They would give text, mask one word, and predict, right? That's how the model was trained. And that's one of the training tasks of a BERT. So this is one of the examples we will do. This is usually referred to as so there's two approaches in the original paper. The masked language task training, right? And then there's the second one, which I think is actually probably a lot of people said it didn't work, it's not interesting, but actually it turns out it's really interesting, right? Because they created this other one called a two-sentence task training. And in the two-sentence task training, they had essentially sentence A and sentence B, and they were just looking, okay, does this sentence follow the previous sentence, right? True or false, 0 or 1, okay? So they would provide sentence A, sentence B through the same BERT, and notice that there's all these outputs which are ignored, and the only one that they care about is this little orange one, which is saved by default as just not a word, but just a thing. It's a symbol, CLS, right? And what comes out here is like a classifier, 0 or 1. So if you think about it, it's a binary classifier, but a binary classifier between 0 and 1 can also be like a score, right? Because you can have a 0.6, such as the probability that is, 0.6 is more likely to be the top class versus the bottom class. Guys, over there. So do you guys see the idea? So here, this model, how does it work? You provide a feed-forward layer, and it just has one neuron. Think about that, right? So one output, right? It's crazy, right? So you have all these inputs, all these embeddings, all of it, but it only has one value. But these became very powerful things called BERT scores. And essentially you can, as I said, if you had a task where a teacher takes a homework, reads it, and then just gives a grade, so this is essentially what this is doing. This is the homework that goes in, and then you get a grade. And this value can be between 0 and 1, and a reward. Yes? Mm-hmm. Because that's a good question, right? Because the transformer has that capability, and how do you so yeah, one option would be, how do we like remove it or something? Or another alternative is, well, we're just training the weights to focus exclusively on this. So remember that the only feedback that you get is from here. You're not going to get any feedback from this. Do you see that? So all the weights they get massively updated here exclusively for the task of this being really good and nothing else. But it works first of all, and you can give it any kind of text here as input, and all it's doing is providing a score, a reward. So now think about this. So initially they did sentence A, sentence B. It seemed almost like a trivial, terrible idea. Like they did the first one, MLM, they were more excited about that one, but they probably wanted to have a second one. And they're like, let's just do this. As it turns out, that's actually the application of this. It's a very useful thing. For instance, question and answer. So now they can give a question here and an answer. And the score tells you what? Oh, that's a good answer for that question. Or it's a good combo. You see that? Versus another question and answer, and they're not such a good pair. And so then the score here is poor, right? 0.20 versus a 0.80. And so now the model, if humans manually look at questions and answers and provide a score, now you have a training set for this BERT. Do you guys see that? If I can also give it like spam, like text that looks like spam, and I can train a model to tell me spam, not spam. And then I can use that, but not just it doesn't just provide a binary value, right? 0 or 1. In fact, it provides in a range. So now it's a ranker. So what's great, that's better, right? Because, just having 0 or 1, okay, you're kind of limited to that. But if I have 10 samples and I get a 0.6 and a 0.7 and a 0.9, that's nice because I'm able to identify these two are better than all the other ones. So it becomes a reward function, which is going to be a key thing when we look at reinforcement learning and reinforcement learning through human feedbacks, which rely on rewards. So this becomes a reward function. Why is this important? Again, I go back to the example. How do you teach a robot to dance salsa? How do you write the reward function? The math for that. It's very hard probably. But you could build, a function like this that looks at 3 videos. It's trained by humans, obviously. Humans do the task first, create the data. Then you use that data to train this model. And now it learns how to say, out of these 3, this one is better. That's the reward. And you can fully automate that process. Make sense? Yeah. So this is a very powerful thing. And so now we're just going to take a look at very simple examples. So this in code, and I am using PyTorch for this. It's going to be very similar to the baby GPT. Okay? So let's go then. I'm going to close this one. Let's go back to table of contents. Click on baby BERT. All right, and it opens up a description. I'm just going to focus on these 2 scripts. So I have this one, which is the baby BERT. We can start with this one. Baby BERT for the mask token predictor, MLM style, right? So these are overly simplified, but technically correct, right? And then obviously remember that these models would have way more layers. This is just one layer, right? Multiple heads. This is just one head. So it's super simplified. And then we're going to conclude with the baby BERT sentence pair score, which is the essential idea of a BERT score, so it should provide a score. All right, so let's start with this one. This is fill in the blank, okay? So baby BERT mask token predictor MLM style. So I'm going to create a collab. And by the way, I'm only doing the inference part, so I'm not doing training or anything like that. Just showing you the architecture of input going in and value coming out, which is really what matters. So let's do notebook. All right, so we're going to go take our time here. So this example shows how to predict a missing word. Okay, so it's the fill in the blank idea. So imagine the cat sat on the mask. And what it should predict is some kind of an ID, right, of the corresponding word. So the cat sat on the chair, for instance, something like that. Okay, so let's go ahead and start. So I'm going to put in a few libraries here. This is being done in PyTorch from scratch. So, the usual torch functions, torch NN, and torch functional. Okay. Then we're going to bring in a few parameters that we have to define here, a few settings. So in this example, the vocab size, we need to have a size, right? Usually the vocabulary size for large language models is like 50,000. To keep things simple, this one just 1,000. The numbers are made up, they're just random numbers. The embedding size is going to be 64 whenever we're creating embeddings. It's similar to what the autoencoder homework is, from 1,000 to 64. So we're just creating these embeddings. FF dimension, this is for the feed forward, so those heads at the end, normal neural net, they have 128. Sequence length is going to be 6, so a short sentence, and just batch size of 1. So just keep it simple. Notice that we're going to have an ID for the mask, which is going to be 103. So let's go ahead and do that. Okay, so now let's look at the input. So here the input is already integers, but it would be like those words. The cat sat on. So the cat sat on. So 10, 20, 30, 40, some IDs, and the mask ID that we don't know what it is. It's a torch tensor. So this is how the data would go in, right? So we have a sentence, and then what happens? The tokenizer will process that sentence and convert it into a sequence of integers, right? So the same idea. So that becomes input IDs, and that's that is what goes into the neural net, which would be based on a transformer encoder. Okay. All right, so now we grab the embedding layers. So we use torch embedding and then embedding here. So NN embedding is a construct in PyTorch that allows you to efficiently map like from integers to embedding. So every word is here, and then this is the representation of it. So that's essentially what's happening. But so for instance, when you're predicting a sentence, right, knowing the sequence of the words is also important, right? So in the past, when you use an RNN, for instance, you would kind of have to predict one, and from that you predicted the next one, but that was highly inefficient. So transformers use this trick called positional embeddings, right? So they create this little idea, and the trick is that they use the sequence length to, so first word, second word, third word, fourth word, fifth word, those become the IDs, the positions, instead of the actual IDs of the word. Okay? But you create and so you can map then from these IDs to a representation of and the embedding size is going to be the same for both, so they can be added together. All right, so that's the trick. So here you can see this is just think of this as a neural network layer, right? So you're going to give it this sentence essentially, and it gets mapped to embedding and then the positions as well. So that creates the token embedding and the positional embedding. So here we have, so let me maybe create, So this just takes, so this is also, by the way, this just creates almost like a function, right? And so then you have to give an input to that function to actually transform it. So the first, let's just do this. That, and then this becomes x, just to simplify it a little bit, like that. Okay? So essentially, first I'm going to take the IDs, right, the ints. They go into this, and now they're going to be converted into embedding representations of the same thing. Okay? Let me move this down. All right, so let's run this one. Okay? Now we can print out the shape of it. And it's 1664. Do you guys understand? It was 16 before, right? Because it was just a sentence of IDs, but now it is 1664. Every one of the 6 words is now a vector of size 64. It's been embedded. And this is very similar to the baby GPT from 520. So that's the same idea. All right. Now, the positional encoding, we're going to look at the same trick that is used for the GPT, which is a clever trick. So here you just create a range, a sequence length, right? So you have 6 positions, right? That's the length of the sentence. So you just create 0, 1, 2, 3, 4, 5. And you see that? And that's the trick. So just like before, we had IDs such as 20, 30, 40 to indicate a specific word. Now we're providing 6 things, but this means the first, this means the second, the third, and so on. So we're keeping track of the positional encoding. So now let's do let me do a print here. And then let's do this part here. I'm just going to call it pause. All right, so now this thing that I just created, this sequence of numbers, right, goes into pause embedding. What is pause embedding? Pause embedding is, I defined it here by using the NN embedding, and it's just going to take the sequence length and convert it into embeddings as well, all right? But based on position. So I have pause here, and now I'm going to do the same thing. I'm going to print pause dot shape. You can see it is also a 1664, right? And so now I have a way to capture the actual IDs as an embedding, but also the positions as an embedding. And because both tensors are the same size, I can add them. And that's the trick, right? So they invented that idea, and it works really well. Okay? So now I have my pause here. And so I just add them. And if I print X, whoops, if I print X dot shape, just like that, it is also a 1, 6, 64, but now it's keeping track of both the IDs and the positional encoding. So that's already there. So you know what word comes first, what word comes second, and so on. And that's important as context for the transformer. So this tensor, the 1 just means one batch. Remember, 6 means the sequence, and 64 is that each one of these is now an embedding of size 64. All right, so now comes the creation of the block essentially, right? And this is, if you notice here, this has the attention mechanism. That's the only thing that this one includes. So remember, this is an oversimplified version of what's described in the 2017 paper. Just but it's got the basic thing. So we create a class, baby BERT encoder. So you can see baby BERT block, it inherits NN module. We have our constructor in it, and then we have our forward function. Okay? So what goes in here is X, which is this X that we just created that has both the IDs and the positional encoding. So notice here, it just one step where we normalize it. Okay? All right, and this is very similar, as I said, to the GPT code. Then comes this function, which is in the 2017 paper, which is the calculation of the attention. So the way that this works is that essentially you take like X times X, right? But you don't actually do the multiplication between X and X. Instead, you're going to, from X, you're going to create something called Q, and also from X, you create something called K, and that's what you multiply. Okay? So let me just go to the Blackboard. Okay, so the attention mechanism, pretty simple. You've got your X, which we've defined currently, that is 1, 6, 64. That's our tensor. But we need, whenever you read the attention paper, it says this thing about KQV. So we need to have KQV, and then we perform these matrix multiplications and so on. But what is KQV? In its simplest form, KQV is just a matrix multiplication of X. So X times, what is it, WK, correct? Set a weight matrix plus BK produces K. Do you guys see that? That's it. And then, so then what is Q? And I probably should be uppercase Q. Q, right? So what is Q? Essentially the same thing, X times W, but Q, right? So we have another weight matrix for this. Remember that these weights have to be learned by the model. Here we just set up like the neural network architecture to do this computation, but the values have to be learned. We have a BQ. Notice it's the same X, right, for both, and that creates K. Or sorry, Q, K and Q. And then we have the final one, V, which is the same idea. We have X times another weight matrix, but for V, and the bias for V. We perform the matrix multiplication, and now we have KQV, right? And then what do? You take K times Q, the transpose, right? And so this is the attention mechanism, essentially, right? So this creates a matrix. So think of it intuitively as you comparing X to X, right? So the words in X are compared to the words in X. So essentially the 6 elements are, you're comparing. So when you do K and Q, it's almost like you end up in this case with a matrix that is 6 by 6. You see that? And so this vector, let's say that represents the word 3, that might be of size 64, is compared with all the other ones, which may also be of size 64. Right? So you see that? That's it. So you perform that task, right? And then once you have this matrix, you want to bring it back to being 1, 6, and let's call this, when you do K times Q, that gives you, let's say, WEI, W-E-I, right? Let's just call it that. And so now you want, the final step is to go back to this dimensionality, So you just perform way times V, and that gives you the final whatever result, let's call it. Okay, so that's the last step in the process, okay, of the attention mechanism. So if we go back to the code, we can see this actually done in the code. And that's how the attention mechanism works. So let's share the screen. Okay, so we can see this here. So notice we define here K, Q, and V, right? And what are they essentially? We use the traditional NN linear, right? What we saw from the autoencoder, remember NN linear is nothing more in PyTorch that H equal X times W plus B. That simple equation is NN linear, but simplified, right? And so we specify here the dimensions for this, right? And so we take X and it becomes Q in the same as I gave the example. So now this becomes like a function. So X just gets normalized to become H. Notice H goes into Q to produce the new version. Then I have H again, but goes into K, right, to produce the new version. This is just a matrix multiplication. This is another way of writing that in PyTorch. So we perform that K times Q that I just described, and this transpose, and then it's divided by the embedding size square root, something like that. That's in the paper. So that gives you, and then you run it through a softmax function. All these details we did cover in 520. So when you guys take 520, for those of you, we'll get into that. But we've already covered all that. So just remember, it runs through the softmax. Now you get this attention mechanism, and the last step is to take that attention times V, where V takes in, it's just H go into V to get transformed, right? And then notice this now has the same size as the input, so we do X plus this, which if you remember, this is called a residual, right? So residuals are a technique that solves the vanishing gradients problem. So when you have very deep neural networks, this is something that we use. And then once you've done that, if you notice, you just have here this X goes into another normalization to produce this H, and then this H goes into FF1, which is just a linear, right? And this was that trick where the embedding goes up to a really high, and so from one layer of this size to a bigger one, and then back to the original size. So you can see that's happening here. So this is like a neural network layer of, let's say, 64 to 128, and then from 128 back to 64. Okay, so this is just what you do. It's adding a couple more neural network layers. Okay, so that's FF1, a ReLU activation, and then that goes into FF2, and again another residual, and that's it. So yeah, so that's so this part. Let me, I guess, go back to the for a sec. Okay, so we did the attention mechanism, right? And attention mechanism. So think of it as you're here in the neural network, and now you just have a feed-forward layer that goes from 64 to 128, and then back to 64. Okay, so, and this is just normal NN linear operations, all right, to transform from one layer to the next. Okay? So all of that is actually pretty standard. Okay, so that just gives you this result here, X. Okay, so that's our baby BERT architecture, okay, using the transformer. So now, we went through a block of transformation, which is essentially just having an attention followed by a feed-forward network. the next step is to instantiate so we're going to instantiate that class, a baby BERT class. We're going to call it encoder. And then we take our X, which we already had ready to go here, right? The IDs plus the positional encoding. And that X is this one, goes into the encoder, and then now we have another tensor, which is actually at this point very much an embedding, right? So if you remember, that's where this embedding would go into the decoder for translation. So it's like we took the, say Portuguese sentence, it just became some kind of strange embedding that would move into the GPT to translate into English or something like that. So that's essentially in the 2017 paper. But now, as they were building the BERT paper, right, they were asking the question, so what do we do? So then they take this embedding and they're going to add a new head for like the masked language model approach. So that's essentially this idea here. So now let's take this code. This is the last part. Okay. I'll move like down here. Okay, so first of all, so here we add another NN linear, remember? So essentially whatever the input is times a weight matrix plus a bias to produce another layer. This one is embedding dimension, which is 64 here, right? And now we make the projection essentially, right, to a size 1000. Because now we want it to, the vector of size 64 needs to predict the word, right? So it needs to have size 1000. So we create this projection layer, and now we apply that projection layer to X, to this X, the embedding. So essentially going from the embedding to something that predicts words, okay? So this becomes 1/6 vocab size. So for each one of the positions, we can predict one of the 1000 words. So this X goes into projection and produces, these are called logits when they're at this stage, usually like a whole bunch of values in a vector of 1000. Okay, and now we have the mechanism where we have 6 things, and for each one we can predict, a vector of size 1000, a word, essentially. So now we take, so here. Okay, so in this step, we want to predict, get a prediction at the masked position. So we only care about this one. We know which one is the mask ID, right? So essentially this is just saying for input IDs, get me the one that matches mask ID, okay, which was 103 or I think something like that. So that's the mask position. Okay, so that was, I guess, 4. And so from logits 4, right? Right, that's where we get, so we had logits. Yeah, we have 6, a tensor of 1/6 1000. So then from this, we just use torch argmax to calculate what is this one? The predicted ID. So it gives me the ID of the largest value in this one particular logit, which is the 4th one in the sequence. And that's the only one we care about. Remember that when we're training, Like your question, right? We ignore everything else and we're essentially just training for this one particular item, right? The masked element. So this should then, in theory, give us an ID. So let's, where is it? Yeah, here. And there it is, 997. Does this make sense, guys? Any questions? So this gives me, you know, a lot of it is straightforward. Um, just to recap, we go from X, the input tensor, through the entire baby BERT block, which does the attention, the feed forward, all of that. So we end up with this one, which I should have printed the shape, X dot shape. Okay, so 1664, okay? Then we create another layer because these are just embeddings. Now they need to have meaning, which means they need to have the capability to take that embedding, whatever it is, and predict the probability distribution of the words for each one of these. So we do this. Here we just define it. Here we apply it. Again, I should have printed the shape. Logits dot shape. Do you guys see that? So it is now 1, comma 6, comma 1000. Because it's no longer just an embedding, it is now, you know, we need the probability distribution over all the words. Right? And the model needs to learn to predict which is the word that's most likely here. And then, but of course, because it's the masked language model, we don't need to predict every word. We just need to predict the masked word. So that's what this gives us. Okay. That gives us I'm trying to think why it's giving me two values here. This is what's tripping me up. Not predicting all of them. Non-zero. Tuple true. Logits. Let me take a look at this. Let's see what this is doing. Right, so mask positions is this tensor. Logits is 1000. This is 1000. One thousand. Yeah, so it's giving me. It's almost like it's only looking at the fourth one, I think, right? But I don't. Batch. I think it might be the batch. It's one, yeah. So I think it is, in fact, the batch. That's my guess. It's mask position. The last dimension, so we look at the last dimension and we just get the value and get, yeah. And then it predicts. Yeah. All right, so this is the part that confused me a little because there's two values here. I would only expect to be a 4 here, right? But I do believe it's because we need to provide the batch number. So I'll have to double check that, unless you guys have an idea. Do you have an idea? It's the batch, yeah, okay, yeah. So because I'm using 1, it seems not necessary, but if I was using batch of 32, this would probably be pretty important. Which makes sense, actually, because I need, okay, yeah, so if I have a batch of 32, not every one is going to be 4, right? It's possible that, the first one is 4, but batches, they're independent, right? So one batch, the first value in a batch is independent from the other one because you're supposed to do things in parallel. So yeah, it makes sense that for the 3rd, I need the 7th position. For the 20th, I need the 6th position, and so on. So it is the batch number. Makes sense now. All right, great. Thank you. Yeah, so as you guys can see, this was the mechanism. It wasn't really that complicated, right? Once you see it, is initially when you think of the idea, you're like, how would I ever do that? But as you can see, it's just simple concept. You take the original embedding 1664, and then you do some kind of a projection back to the vocabulary space, vectors of 1,000. You apply it, then you select which batch, I guess, and which element in the sequence you need. You extract that. Remember that when you're training initially, it's going to predict something that's incorrect, right? So it's going to predict something, it's going to compare to the real, take that difference, and do what? Calculate an error that back propagates, updates the weights, and it keeps doing that so that eventually, right, as it's learned to do this task, what's going to happen, it's going to predict the word. When that word is compared to the real word, they match, right? And so that essentially it starts to become a good model. Do you guys see that? Are there any questions on this? All right, so if that makes sense, that's really great. Now we have enough time to cover the other example. They're very similar, right? And in fact, really, the only thing that changes is the head. So I can skip the whole attention this time, right? Because that's going to be the same. But let's, so in this one, notice that what we predicted is a word, right? So remember that what this means is it predicted 538 with the tokenizer. We would figure out that that probably means the cat sat on the chair, most likely, or something like that. That's this example. All right, so now let's do, I'm going to close this collab. And now let's look at the other very interesting idea of using a BERT. Instead of a mass token predictor, we're going to look at the task of a baby BERT sentence pair scorer. So this should give us a score, which, like I said, is the basis for our reward function when we don't know how to write the math for the reward function. And so we can just train a model to provide a score for us. So we'll look at like Q-learning later in the semester, and we'll look at some ideas like that, SPO, score-based optimization, things like that. You can write equations to produce the scores. Heuristics work. DeepSeek, I heard, used a whole bunch of heuristic rules that, to provide rewards. So you don't always need a large language model or a neural network, but, I'm just giving you this idea that you can do that. All right, so let's now open Colab. Okay, we'll wrap up with this. Let's add a few segments. Okay. All right, so baby bird sentence pair score. This shows how to encode, let's say, two segments. Could be question and answer. It could be old sentence, new sentence, or next sentence and previous sentence. It could be just normal text, right? Like a paragraph. Is it spammy or not spammy? You can see that a lot of this is, this mechanism works for all those things. So let's go ahead and do this simple example of the original example in the 2019 paper of does sentence B follow sentence A? As you know, if you have a book, you grab a sentence in the next sentence, and that becomes an example of sentence B follows sentence A, or you take one sentence and then randomly select another sentence from the book, and obviously they don't follow each other. So that's how this was trained. This is called, like, I think, semi-supervised or self-supervised, right? Self-supervised. All right, so let's go ahead and try this one. As I said, I'll skip a few parts given that it's pretty similar. All right, so we've got our libraries. All right. And then we have a few new things here. Okay, so we have the same vocabulary size, 1000, the embedding is 64, the FF dimension is 128. The sequence length here does need to be a bit longer, right? Because in the previous one it was 6, but it was just one sentence. Here we, in theory, have like a question and answer, two sentences, etc. So we have something like 12, and this will have a few additional symbols, right? So before we had the symbol mask, right? And that was 103 or something. Now we have other IDs that are exclusive to this task. CLS being the first one in the sequence. And that allows you to then use that first input so that something goes in all the way to the output. And that can be the thing that you predict. And then we have this symbol called separator, which is what we put in between the sentences. So sentence 1, sep, sentence 2. All right, so this is how they did it. Batch size is 1, same idea. All right. So now let's think about this one. So this, notice, will have the normal token embedding, the positional embedding, but it also has a segment embedding, whether it's segment 1 or segment 2. All right, so notice here we have an example. We have CLS, that's the first symbol for the prediction. The cat sat on, separator, and then it was some other sentence, it was soft, and maybe some ending symbol. All right, so that the equivalent of that in inputs, if we used a tokenizer, would be something like this. Okay, so this should be the first sentence, the zeros, and the one should be the second sentence. All right, so we need to provide that there, and then this needs to be encoded into an embedding, essentially. All right, so let's take a look here. So we ran that. So now we create the embedding layers just like we did before. Okay. So we have the token embedding layer, which goes from vocabulary size 1000 to 64. Then we have the positional embedding, just like in the previous example, right, which indicates the position in the sequence length, which is 12, from 0 to 12. And that produces an embedding of size 64. But now we have this other one, segment embedding, which has 2 for the, is it sentence 1 or sentence 2, with the ones. So let's create that. And then we can print the shapes. So this one This is the same thing we did before. So let me actually copy this whole thing. Let's do this in parts. All right, so I have, I can do this first. Positions, I'm going to print it just like I did before. You can see it's just a list of the position. Is it the first, second, third, fourth, and so on. You keep track of that. Then I'm going to do, I'm going to call this X. X, like that. Okay, so this is the input IDs, which was the numbers here, right? These IDs. And I'm going to do print x.shape. So it's 112.64. So now this is the representation of the words themselves, which is what we did in the previous example, right? That's what I just did here. Let's call it x1. Token embedding is x1. Okay, then the positional embedding, that's the same thing that I did before. Let's call it x2. Right? So x2 takes in positions, right? So just like we did in the previous example, each one of the positions gets mapped to an embedding of size 64. Let's print the print x2 dot shape. Okay, 112.64. Notice they both have the same thing we did before. They get added. So now the new element that we have in this example is for the segment IDs. So the segment IDs are this one here, right, indicating the whether it belongs to sentence 1 or sentence 2. Do you guys see that? So that's essentially, so we need, this is kind of like your homework, right? So you have some kind of a semantic type of thing, belong, not belong, something like that, a little bit. All right, so but let's look at it in terms of the dimensions. All right, so we need this one. We're going to call it x3. Okay, so I'm going to do x3 here. Okay, this is going to be segment embedding. Right, segment embedding. I think I had an error there. So segment embedding from 2, there's only 2 options, to size 64, correct? For the 12 elements. All right, so embedding, positional embedding. Yeah, I had it as segment embedding here. Did I changed something, didn't I? Hmm? Pardon? Okay, that's what I missed. Yeah, I thought that there was something wrong. Okay, so I had it correct then. Yeah, I'm glad I checked. Sorry. So I changed this and confused myself. So let me just corroborate this one. Right. So it should be two. Yeah. Okay. Thanks. Yeah. And then here, for some reason, I did this wrong. So X3 should be whatever this is, right? Segments. Yeah. Yeah. Right. So now I grab these segment IDs and I'm going to map them according to this function here, this NN embedding, which follows kind of the similar approach to these, but I only have two values there. So, hmm, maybe I didn't run this. It worked this time, so I hadn't updated it. So now let's print a shape, x3 dot shape, and it is for every one of the 12 in the sequence. Now it has its own embedding, but it is dependent on the whether it's a 1 or a 0, correct? And that indicates whether it belongs to, so it's a semantic mapping as, the homework, as I said. All right, so that was the hard part. Then you just add them together. So that's going to be this part here. And if you print the shape of this, that's the trick, right? You can notice how clever this is, right? You can create tensors of embeddings, and then just add them together. You can have positional encoding, semantic encoding, segment encoding, whatever you want it to be. So x dot shape. So I think we can still finish. So that's 11264, right? Then the other part, this is exactly what we did before, so I don't have to explain any of this. So just the attention mechanism, that good stuff, takes X and produces an embedding. If we print that embedding, it will also be 1 comma 12 comma 64. So we're there back at BERT from 2017. So now we need to add some kind of a head. And this is the last part, so that we can predict a score. Okay, so let's bring it down to like here. Okay, so essentially here, we're just going to pick the first token. So see it. So we grab this X, right? We're at the, input went in, went through the whole transformer. We're at the output, right? We have the embedding. And if, we do this, the CLS token from X. So essentially, if I print shape here of CLS embedding dot shape, we get just one vector of size 64 for the first actually, for the first of the outputs. So here. This one here. Because the first, we're slicing, right? So the first one means all the batches, there's only one. The last one means old in the dimension, 64. But out of the 12, we just want 0, which is the first one. So essentially this one. Do you all agree? So we grab this one here from the, and we don't care about the other ones. In fact, it's being wasted, right? And so, yeah, so we grab this one. And so what we need, we're here essentially, and now we need something like this to produce. So we need a projection layer to 1. Let's see. And we're almost done. So you can see here I have my vector of 64. And guess what? What do? N in linear. N in linear does all the heavy lifting, if you remember. Whatever this is, times W plus B to create the next layer. So this one is of size 64, correct? Vector of size 64, and guess what? It gets projected to just one neuron, not 64. And so now we have the score head. You guys see that? All right, so if I print on this one, that's provided. And then we just use something like a sigmoid. So now, remember that here we're just defining that layer, but we haven't applied it yet. So we're going to take CLS embedding, the first one, run it through score head, and now it becomes just one value, one neuron, and then we use a sigmoid activation function, which if you remember, sigmoid goes from what to what? 0 to 1? 0 to 1, right? And so it goes from 0 to 1, and guess what? You have your score. And now you can create rewards for your models. So if we apply it, okay, and this is the same, I just copied it. So now if I look at score item, 0.22. Obviously I'm using random data, so this is just predicting some value, but now, you would, let's say somebody, and we'll finish with this, a human came in, had a question and an answer, they both go in, but when they actually did it manually, so they looked at a question and answer and said, oh, I give this a 0.22. And then look at another question and answer and, oh, this is really great, I'm going to give this a 90. So now you come to the training, so what do? You give the question and the answer, it goes into the model, and the model predicts, I don't know, 0.30, right? But that prediction is compared to 0.90 that the human gave. All right, so you calculate the error, back propagate, update the weights. Do you see that? And that's how it's going to learn how to, when you give it a question and an answer, to give a reward and simulate what a human can do. That's it. Does that make sense, guys? Any questions? All right, so we finished. Yeah, so we're only a minute over. And that's it. Go ahead and read through this material. There's more notes, and I'll be updating this. And yeah, that's it. So we've concluded today BERT models. We did the baby BERT. We discussed both approaches, BERT scores, and we learned how to fine-tune. Next week, we're going to move on to a few other things. All right. Please don't forget, you have a homework assignment now. Start working on that. You have 2 weeks to complete. All right, guys, so we'll stop here for today.